I just realized the recording didn't have my voice in it. So, well, we didn't do too much anyways, but yeah, my recording did not have the voice in it. Okay, now we're good. So this is, yeah, this is just.
Okay, I think I got it.
Yeah.
So that delta x can be replaced by h sine theta, like we discussed,
Yeah.
and then that gets transferred in, and then just get rid of the theta. I mean, the sine.
Yeah, and then that'll be turned into that, right? That'll
Mm-hmm.
be turned into that, and then this will be. Wait, no, but it's still times h. This is still gonna be.
It's kh squared theta because for small angle approximations, sine theta is equal to theta.
But shouldn't the torque be the distance from the pivot,
Mm-hmm.
k times delta x? Delta x is h sine theta
Yeah.
times sine theta. So this will be sine
Mm-hmm.
squared theta. Because this is still times sine theta here. This is essentially what we have.
Oh.
You see what I mean?
Okay.
Or wait, would the angle between them? No. Angle between them wouldn't be 90 for any reason. Oh wait, no, yeah, the angle between them. They're different thetas we're talking about, I think. Yeah. We're talking about different thetas here. That's a different theta. So the angle, but that theta here, that theta is this angle, which is 90. Sine of 90 is 1. So that goes away. Because that's this thing you multiply by here is the angle between the two vectors. So here we have this vector, and here we have this vector. This is the force vector. That's the radius vector. So that's 90. So it's times 1. And now we have our kh squared sine theta, which is approximately equal to kh squared theta. Okay, that's the first. Oh, but they didn't lose the negative. I lost the negative because I took the absolute value. Somehow they didn't lose the negative.
Probably because of the direction.
Direction of what?
Is counterclockwise negative? Is that how we did it last semester?
Oh, yeah. And that's, but this is, hold on. This force is pushing this way. That's clockwise. Or is the force pushing this way?
The force is pushing towards the wall because we're looking at it from. Yeah, okay.
Yeah, I see. Okay, so the torque from the wall is negative kh squared theta. Hopefully that kind of makes sense how we got to that. So from here, I should just remind people, because I need a reminder too. Torque, I can't write torque for some reason. Torque is the distance, the magnitude of the distance, times the magnitude of the force, times sine of the angle between them. Okay, that's the, I should say this is the magnitude of the torque. I guess I'll leave that off. The distance, so that's h, times the force, times the sine of the angle. Okay, now finally, we also need the torque from gravity. Okay, the torque from gravity is, again, okay, so the distance between them is L. Yeah, L. This is an H, by the way, not an L. This is a H. So we need an L here for the length, and now we need the force. So the force of gravity is just mg, the mass times gravity. And now the angle between them. So what's this angle here? Well, that angle there is 180 minus theta. Yeah, because this is theta. I should draw here. This, different color. This is theta. So this is also theta, right? That's also theta. So that angle. Oh, no, that's still just theta. Sorry. That's still just theta because I was measuring the wrong side. This is what I was measuring. This is actually what we count. This is what we want. So it's actually just theta. So we just want mg sine of the angle between them, which is actually theta this time. And so this should be L mg theta, approximately equal. So there's our two torques. So our two torques were the sum of the torques. Wrong place for the sign. The sum of the torques are negative kh squared theta, and then well, we need the sign on this one to be correct. So the sign, the torque. Let me think for a second. The force is acting this way, yeah. So it would be forcing. The force is acting down here, so it's kind of like it's turning it that way. So it's going to be negative, the torque. So this is negative LMG, so we minus LMG theta. Okay, we got this, right? That's what we got. We got the sum of the torques. Well, the sum of the torques are equal to the inertia, the moment of inertia, times alpha, right? The angular acceleration, kh squared theta minus LMG theta. Okay, what's the point of this? From here, okay, we put in that, and we're trying to solve for omega. How do we know? Let's just see what they do here. Okay, next thing we got to figure out is how does this turn into this? How does the acceleration... Oh, I guess that's the no. Yeah. Oh, because it's sine? So for small angles of sine, theta equals theta. Okay, the next thing we have to figure out is why does... So what they do is we have this equation. Put in ml squared for I. And then our goal is to rearrange for omega. Because once we do have omega, we can just find the frequency like this, right? It's pretty simple. So the omega... For them, in the solution, it appears here. Somehow, angular acceleration is negative omega squared theta. Someone gonna say something there?
I don't understand what's negative though.
Why is it positive? Why is it omega squared theta?
Oh, with dimensional analysis, it makes sense because that's just gonna be a negative. As to the -2, right? And then it's just gonna be multiplied by like a value, like a radian value,
yeah,
right? Or like meters, or like whatever we're looking for here. And then that'll be our angular acceleration, like radians per second squared. Is that the unit that we use?
Yeah,
right?
radians per second squared. Yeah,
that makes sense, but I don't understand why it's a negative.
I also don't understand. Well, yeah, why is... Hold on. Yeah, no, I don't understand why it's... I don't understand how they even know this. Am I just forgetting something? Or
like, it works.
It works.
But, like, I don't know either. Like,
how would they figure that out?
I don't understand it either. Like, wait. Look at our equation. Wait, I think I know why.
Okay.
Okay, so... Okay. Our theta is like our our theta here is like our amplitude, right?
Yeah.
And our our omega squared is like just our omega, and that's like our A max equation. And
yeah,
like because the whole situations are A max. I don't understand why it's negative though. That's what I still don't get.
So this is from simple harmonic motion. A max is A omega squared.
Yeah.
Sure. Why do we have the maximum acceleration? Just because it's... Well, I guess we're assuming it's constant acceleration? No, it would be constant acceleration because it's no, it wouldn't be that. So what's happening here is we're assuming it's constant. Well, we're assuming it's constant, but we're also assuming it's always the maximum acceleration. Is that because of small angles? Possibly because of the small angles. But I guess that's how they find this. But then A is theta. Amplitude is theta. Yeah, I guess so.
So I think it's negative because like when we derive the formula for this simple pendulum, you get d squared theta by dt squared equals to minus gl minus g divided by l sine theta. And you take that g divided by l as omega, so it's minus omega sine theta, and theta is hence a small angular approximation, so that becomes minus omega theta, or
From
minus omega squared theta.
where did you start? Was it on this page here somewhere or?
No, no, actually, like in our notes when we derived the formula for this simple pendulum,
Yeah.
so what we derived finally was d squared theta by dt squared equals to minus g by l sine theta.
G by L sine theta. Oh, okay.
It makes sense if you write it down.
Yeah.
Hold
D...
up, I'll send the screenshot of the slide. I found it.
Okay, you found it? Okay, yeah. In homework help?
Yeah, I'll send it in homework help. Okay.
So that's this.
Right, yeah, this one.
Yeah.
So you substitute g by l as omega squared.
Okay.
Oh, okay, got it. I see what you mean there.
Yeah.
Okay.
And using small angle approximation, you get d squared theta by dt squared equals to minus omega squared theta.
Yeah, exactly. So dt squared equals minus. Okay, well, I'm going to explain it a little bit now too. G over L. So if omega is the square root of G over L, then this is omega squared, right? So we can just say this is minus omega squared theta. That's right, this is equal to that. Because sine theta equals theta for small angles. And then...
So it's not a max. Okay, yeah, it's not that equation.
Yeah, it's not that one.
That doesn't make sense. Okay.
Yeah. Okay, so then now we know this much. Okay, so I'll keep going from here. I'll keep going from this point here. So we have our moment of inertia times alpha equals this stuff. Moment of inertia is m, the mass, times L squared. Okay, and this is still alpha equals negative kh squared theta minus L mg theta. Then I want to replace alpha with negative omega squared theta. So this is negative ml squared omega squared theta equals negative k. That's an h squared theta minus L mg theta. And now we just rearrange for omega. Oh, I guess I can divide everything by theta. Yeah, I can divide everything by theta. So I'll do that. So it's going to be negative ml squared omega squared equals negative kh squared minus lmg. And now I will divide everything by m and flip all the signs. So L squared omega squared equals negative k, positive k over h squared over m plus lg. Divide everything by L squared, so omega squared equals kh squared over m L squared plus g over L, and then just take the square root. Omega is the square root of g over L plus kh squared m L squared, which is essentially what they wrote, I'm pretty sure.
Yep. We're good. Yep.
Wait, why did they get 1 over 2 pi in the front, though? Oh, this is
because
omega.
we're solving
this is
for
omega.
frequency.
Yeah. This is omega. And then frequency is omega over, or 2,
no, you're right. Omega over 2 pi.
Yeah, is it? Okay. Is omega over 2 pi. So then, yeah, okay, that makes sense then. So 1 over 2 pi times the square root of g over L plus kh squared m over L squared. And there we go. Yeah, okay, that makes sense. Okay. So there's our answer. That's frequency. So let's try to see from the question, how would we get to that answer? So okay, we need to find the frequency of vibration for the system for small values of the amplitude, so small angular approximation. Frequency of vibration is like how long it takes to do, not how long it takes, but the frequency of one full vibration like that. One, like, you know, how many times that happens per second. So we know that, and I'll jump to the end here, we know that frequency is omega over 2 pi. Okay. We also know that this here, we also know this, okay, that the angular velocity, angular acceleration equals negative omega squared theta. So this is a good formula to know. Okay, that's good to know. We now have an equation that will get us omega squared. So let's see if we can get the angular acceleration in terms of the things we know here, which was L, H, K, and all that stuff. Okay, we can find angular acceleration using the fact that the sum of the torques equals the moment of inertia times the angular acceleration. Okay, so let's do that. Let's find the let's find the, and I can sub negative omega squared theta right now, or do it later, whatever. Anyways, we got to find the sum of the torques. So that's what I did here. Find the sum of the torques, and I'll color that in. So this is finding the sum of the torques. I guess over here too, so I'll include that. Right, find the sum of the torques. And then from there, we can sub everything back in and solve for omega. Would I have thought of that without seeing Chegg in front of me? And also the help of everybody here? Probably not. But I guess I see that it can be done. And this is not helpful, what I wrote up here at first. So I will just erase that so people watching the recording can, yeah. So any questions about this one? I'm sure it's confusing. It'll get easier once we get to chapter 16. The first questions are not too bad.
Yeah, I just got one question regarding why we took the second torque as negative.
Yeah, the second torque, the gravity.
Yeah, that one.
Well, so here is this vector, what is it? Radius vector, right? I mean, it's in this direction. Anyways, it's here, really. It's like that. And here is our force vector. So you can see the force is acting this way essentially, right? If you pull down on something like that, it's going to start moving this way, right? Does that make sense? If you were to apply this force down like that, the thing is going to swing this way. So that's
I get that.
That's counterclockwise. So counterclockwise is negative.
Oh, okay. Yeah, makes sense.
Right, that's why I put a negative sign. The same thing because this spring is going to be pulling back this way. So the torque is also negative. So there's two negative torques. Okay, any questions? Let's move on then. Let's see, what's this one? 35. So next one is 39. But of course, anybody stop me if you have any questions.
Wait, can I just see the final answer for that one?
Like that?
There you go, thanks.
Okay, no problem. Okay. So 39 looks like this. Whoops. Nope, that's the question again. Okay. So, a ball of mass m is connected to two rubber bands of length L, each under tension T as shown in figure that. The ball is displaced by a small distance y perpendicular to the length of rubber bands. Assuming the tension does not change, show the restoring force is negative 2t over L times y, and the system exhibits simple harmonic motion with an angular frequency of that. Okay, so the restoring force, I guess, is the force that acts on the ball here to bring it back to equilibrium. Okay, well, what are those forces? Well, there's the what are those forces? The force of tension, I guess, in both strings. Guess so. So I guess no gravity. It doesn't actually say no gravity, but I think it's no gravity. Or maybe we just don't have to. I don't know. We'll see. But what are the forces acting on it up here? Well, there's the force of tension and the force of tension. So I think they set a small distance y here because they want this to be a small number so that this angle is a small angle. That's just a hunch. So let's see if that is helpful. So what's the force acting here? Well, it's the force of tension, which is T. Okay. Oh, and that's all. The force doesn't change. So the sum of the forces acting there is, well, it's equal to MA, but we don't have, well, okay, MA, whatever. One of the forces is T. Yeah, not related to the, hold on. We don't know any of the accelerations. I guess I could do the sum of the forces in the y direction. Not equal to MA, just what is the sum of the forces in the y direction? So the sum of the forces in the y direction is, does that even make sense? Would the tension not change? No, the tension would change. Okay, anyways, what's the force of, that's theta as well. That's theta. So, so let's start with this force here. Okay, the acting in the y direction is L, no, not L. What am I talking about? Tension times sine theta plus, again, tension sine theta. So 2 tension sine theta. And then, yeah, I think that this will be it. And then the sum of the forces in the y direction is not part, in the x direction is not part of the restoring force. So now we just know that the sum of the force in the y direction is 2t sine theta, which is not quite.
Yeah, we can just convert sine theta to y by L.
Y by L?
Yeah.
Why by L?
Because
it's,
like,
yeah, I see, okay. Yeah, because sine theta, right, so opposite over hypotenuse, right, so it's going to be y by L. This up here is L, right, so we can just go right away here and say this is y by L, and it's in the negative direction, so I guess it should have been negative in both cases there, yeah. And there we go, negative 2ty by L. Okay, we got that much. So the restoring force is negative 2ty, not t sub y, this is ty. Y is that little displacement divided by the length. So what I just did here is that sine theta equals y over L.
Did you get 2t again?
2t because it was here, yeah, you know what, I should rewrite.
What's the tension? Right, because there's 2 bands?
Yeah, pretty much what I did was I said sum of forces of the y direction is negative t sine theta minus t sine theta. Right? And then this was negative 2t sine theta. And then I used sine theta equals y over L here. Right? And then, yeah. Does that make sense?
Mm.
that. Okay, there you go. So we got the restoring force. The system exhibits simple harmonic motion with an angular frequency of that. Okay. So I guess we have to find the angular frequency. So we can do that. Like the last question? Maybe? I'll try. Try to do like the last question? Yeah. So in the last harmonic motion. Wait, no, last question was a pendulum. Okay, so we have more complicated things happening.
So what I think is like we needed the way we took the sum of the forces in the y direction, continue from that, and then say that MAY equals to 2t sine theta 2t y by L.
Yeah, negative 2t y by L equals MA.
Yeah, and then take the m to the other side.
Oh yeah, negative 2. Yeah. Okay, I see. Negative 2t over MLy equals a.
And this is d squared y by dt squared. And so
Yeah, this is negative 2t over ML. This is y of t equals d squared y over dt squared. So now we can just take this, and that should just be, it's just the square root of that. Yeah, it's just the square root of that. So remember the formula is like, if you see something like this, then the omega is the square root of the thing, 2t over ml. And that is what we got here, 2t over ml. Yes. Okay, thank you for that help there. Yeah.
But why didn't we include gravity, the force of gravity, in our forces?
It didn't really. So what's essentially happening is you have like a bead and you're pulling it really tight, right? You're pulling it really tight. So the gravity isn't like adding to the motion here. It's the pulling it really tight that's happening. So when you like flick it, it's gonna like vibrate back and forth. But the equilibrium position is just the equilibrium position. It's just like by pulling them completely straight tight. The gravity isn't changing that position, so I think that's why you don't consider it.
Oh, okay, so it's just negligible.
Yeah.
Right.
Yeah.
And where did G of T come from?
That's y. Sorry,
Where's that Y of T?
Y of T.
That makes more sense. Sorry.
Don't worry, that's my fault.
A quick note about that, what the last person said. If you remember from our the first lab, we showed that gravity doesn't affect our amplitude, our omega, or anything else that that we analyze in simple harmonic motion. So it wouldn't have even mattered if it did if gravity was applicable here.
Mm-hmm. There you go.
Okay.
Okay. Let's take a look at the next one, number 40. Unless anyone has any questions, I will answer. Okay, number 40. Consider the damped oscillator in some figure. 15.9. I have to go find that now. Hold on. Sorry, 15.19. 15 point... What? Oh, I have to actually go in the text. 15.19. Okay, there you go. So
Sorry to stop you.
Yep.
Just going back to that the last question
Yep.
that we just did.
Yep.
Just that one step. Yeah, no, go back down. Where you have the negative sign and YT. So when we take the derivative or the square root of that, where does the negative in the YT go?
You're asking where does
So
this-
from
this
where you
and
go
this go?
from the
Yeah, this is just, so this is like a differential equation that we have here, right? And so the solution to the differential equation is some sort of function. It's like y as a function of time, right? But all we need is the angular frequency. That's all we want. That's all we care about. And just like before, like when we were, if I look at my notes here, my actual notes, like just like over here when we were like at first at the beginning of the semester deriving the formula for like x of t equals a cos omega t plus phi, right? We saw
Okay.
negative k over m x of t equals this, right? Very
Mhm.
similar to what we have in front of us. And the angular frequency is k over m. K over m. Square root of k over m. Square root of k over m. So you ignore
I see.
just the angular frequency is negative. You get rid of the negative and the x of t. You just take the square root of the number.
I see.
K
Okay.
over
Okay.
m. So we're doing the same thing here. We just want the angular frequency, so we just take the square root of 2t over ml.
All right then. All right.
Okay, there we go. Okay, so now number 40. Consider the damped oscillator illustrated in that figure. The mass of the object is 375 grams, so m equals 0.375 kilograms. The spring constant is 100, k equals 100 newtons per meter, and b, which is the, whatever it is, I forget what it's called, but how damped it is. So the b is 0.1 newtons times second meters. Oh no, Newton times seconds per meter. Over what time interval does the amplitude drop to half its initial value? Okay, so for this one, I'm going to need my section on the damped harmonic oscillator. And then the amplitude is a function of time now. So we can write, because it's damped, so it's going to get slower as time goes on. Like it's going to get smaller as time goes on. So this is AI, the initial what's it called? Amplitude. And then times e to the negative bt over 2m. So that's our amplitude as a function of time. Well, what we want is the time that it takes for the amplitude to drop to half its initial value. So essentially, we want ai over 2 equals ai e to the negative bt over 2m. Great, and now we just want to solve for t. So we can cancel these. Those cancel. And then it's just going to be 1/2 equals e to the negative bt over 2m. Okay, I'm going to do ln of both sides. So ln 1/2 equals negative bt over 2m. I'll write it like bt over 2m. So that oh no, I was going to say the over 2's cancel, but they do not. So it's going to be negative 2m over b ln of 1/2 equals t. Ln of 1/2 is negative, I guess. Yes, it is. Okay, good. So it works out. So 2 times 0.375, right? That was the mass. 0.375 over b. B is 0.1. Times ln of 1/2. So, I still got a negative number because I forgot a negative sign. So t, I got to be 5.2 seconds. This was 40, which there are no answers for, so who knows, but that seems right to me. Maybe someone wants to check. Maybe could someone check if they have the answer on Slater for 40 on the text? I'll keep going. Maybe someone could look that up. What if, over what time interval does the mechanical energy drop to half its initial value? Okay. The mechanical energy. So that's like the sum of the potential and the kinetic energy. Well, of course, this is without it being part of the system. So yeah, okay. So what we're looking for is so the total mechanical energy, which I can't find here. There we go. Yeah, the total mechanical energy equals 1/2 k a squared, right? That's how much is coming in. We'll call it ai squared. And we want to know for what value of t E total, what does it say? The total mechanical energy is half. So we want E total over 2. So this isn't, I should be clear, this isn't like I'm continuing on here. This is the second equation. We're looking for, I'll call it ET over 2. For what value of t, we want this as a function of time. Yeah. So as a function of time, it's going to be 1/2 k a of t squared. Okay. So, you know what? Actually, I could have done that here. So let's do that here. This is a of t squared. So now we know that E total is a function of time. We want to know what when does it get cut in half? So I say, when is E t over 2 equals 1/2 k a of t squared? That should work, I think. I feel like something I'm missing, but okay, let's just keep going. So, well, again, what's the a of t? A of t is this. A of t is that. So I will highlight that. So that goes here. That is squared. So 1/2 k E total over 2. Okay, well, this cancels. This cancels. So all we have left is, no, we're solving for t. Yeah, okay, so we can still say E t equals k ai. Now, I'm going to have to do something with this ai, I know. But for now, it's okay. It's just E, oh no, this is actually squared up there. So it should be clear, but yeah. E to the negative bt over m. Now that ai, no, this isn't going to work. What am I doing? I'm doing something wrong here. This is the total energy as a function of time. Well, this is the total energy. Oh. No. Let's get the total energy as a function of time again. Total energy as a function of time is 1/2 k ai squared e to the negative bt over m. Don't need brackets. Okay, that's the total energy as a function of time. The question is, what time interval does the mechanical energy drop to half its initial value? So if at t equals 0, that's the total energy. Right? At t equals 0, t equals E of t at t equals 0. This is 1/2 k ai squared e to the 0, which is 1. Okay, but now we want to know E of t, and we want to know when does E of t equal the total energy divided by 2. For what value of t? So this is essentially what I'm asking is I'm saying, when does 1/2 k ai squared e to the negative bt over m equal to, this should be the initial total energy, which we just said was 1/2 kai squared over 2. Okay, now I solve for t. I think. Let's see. Negative bt over m equals 1/2. So I take ln of both sides. Negative bt over m equals ln of 1/2. And t equals negative m over b ln of 1/2. T equals, let's see, negative 0.375 over b was 0.1 times ln of 1/2. I got 2.6 seconds. Okay, that was just confusing to think about. Did someone find it on Slater, number 40?
Yeah, you got both right.
Both right? Okay, good. There we go. Happy to hear. So, any questions about this one? This was weird. I know. I kind of messed up halfway through here and had to rethink it, but so this part is
We'll
kind
go
of,
over that because I may or may not have went AFK for exactly the amount of time you were explaining.
yeah. Okay. Yeah, I'll explain it over. And yeah, that'll be good. So, did you get the amplitude part A? Oh, we didn't do part C yet, but did you get the part A?
No.
Okay, I'll just explain yeah, it's good. I'll explain the whole question. Okay, so when does the amplitude drop to half its value? So the amplitude as a function of time is this. So we want to know, when does a of t equal the initial amplitude over 2? Right.
Mm-hmm. Yep.
So solve for t, and I got 5.2 seconds.
Okay. Mm-hmm.
Now for the next part, this is for part B, starting here. We want to know, when does the mechanical energy drop to half its initial value? So to do that, we need to find the mechanical energy as a function of time, right? So that would be this. Although I think I can erase all of this. This is all kind of useless. Yeah, this I didn't use any of this because I was kind of confusing myself halfway through. So you can kind of think of it like this. Oops. So E of t is 1/2 ka squared, right? But a is a function of time. So I can go down here, right? I can go down, and this is actually written as a function of time, right? Because a of t is ai e to the negative bt over 2m, but this is squared, so it looks like this. Okay, so that's E, that's the total energy as a function of time. Now, what is the initial total energy? Well, it's this, right? It's this,
Mm-hmm.
where t equals 0. Now I'm going to take, I want to know, when does E of t, right, the total energy as a function of time, equal the initial total energy, so this is technically the I, right, divided by 2. So I just sub in the function like this. I take this function, put it here, right? And then here, this is ETI over 2. Well, we just said ETI was this, right? So I'm going to put that over 2. Lots of stuff cancels. Right?
Okay.
And then now I just have this. I solve for m.
Okay.
Solve for t. Sorry, solve for t. And then
yeah, got it.
I get that down. Okay, so how does everybody feel about that? Good, I hope.
So what if we were to follow through with this question without choosing the time interval at t equals 0 and didn't have the e raised to the power of negative bt over m to cancel out? What if you just had exactly that equation, 1/2 of kai squared e raised to the power of negative bt m equal to the exact same thing, but just divided by 2? Would it still be solvable, but just more complex?
Like write this over 2?
So this equation that you have right there, your first line.
This here.
Yeah. What if you have that equation set equal to the exact same equation, but just over 2?
Oh,
And then you
everything
have
over
to
2.
over t. Yeah,
Everything over 2.
So on the right side, the exact same thing, but just over 2.
Yeah.
I just want to know, would it still be solvable, but it just would be a bit harder because you got something raised to the exponent of the variable you need to find on both sides of the equation?
Well, hold on. Would we have that? We would have. Oh, because you'd put well, you still need to know it's half of what though, right? It's half of what? So it's half of
So
the
that's-
initial amount.
Okay, so
that
that's
make
why
sense?
you said table.
Yeah.
So- okay. So would it be possible to set the initial amount at t equal to 1 or t equal to 2?
Yes. Yeah.
Or do we?
No. That would
Okay.
work. You could do that. Yeah. You could do that.
Okay, cool.
You'd have a little more complicated of an expression. But
Yeah.
Yeah, it would work still.
Okay.
That would work still. Okay. Good.
But with that, you'd have to know like velocity because you were also calculating kinetic energy, right?
The
Because-
total energy doesn't change though. The total energy.
Yeah, but it's just, the reason we do like 1/2 ka squared is because it's easier to calculate potential energy than it is kinetic because we need to know
Yeah.
velocity for that.
But
right?
no matter what, at t equals anything, the total energy stays the same.
Mm-hmm.
We're not looking at potential or kinetic here. We're looking at just the total energy. So
Okay.
I think it would work still if you chose t equals 1.
Okay, but you would just have like an extra term for kinetic energy, right?
I don't think so because you would just have the total energy. We're just considering total here. Right? This isn't potential energy. Even though this is calculated, this is the potential energy at the maximum. Yeah, that's right.
Mhm.
Right? But this number, this E total is correct everywhere, not just at the peaks, not just at like the edges.
Oh. Okay, I got it.
Right? It makes sense. Okay, and did I do part C? No, I didn't do part C yet. Oh yeah. Okay, so show that in general, the fractional rate at which the amplitude decreases in a damped harmonic oscillator is 1/2 the fractional rate at which the mechanical energy decreases. So we want to show that the fractional rate, so decrease per time in the amplitude, so delta A per time equals, or divided by 2 equals delta E total over T. Is that what I'm showing? Show that in general the fractional rate at which the amplitude decreases per time, I guess, in a damped harmonic oscillator is 1/2 the fractional rate at which the mechanical energy decreases. Or no, this should be 2 times this is that. Yeah. Sorry, I got my fractions wrong there. Okay, I think this is what I'm showing. I think that's what I'm showing. For part C.
Makes sense to me.
See what the answer is in the book. Oh, we don't have the answer.
Well, don't we have equations for both of them? Because a over a to t is just the function a over t, the amplitude over time, and then we have our equation for energy over time as well.
Yeah. Do they want me to take a derivative? Because it's
I don't think so.
it's just
Because
that
we
this
still
can,
we have our we have our equation for amplitude over time and also energy over time. We calculated before.
not over time though, as a function of time, right?
As a function of time.
Yeah. But
Mhm.
this is delta ET. So
Well, if they want the rate of change of A, then we should
Oh.
take the derivative of our A of
Yeah,
t.
derivative.
okay, I think that's what it. So 2 dA by dt equals det by dt. Okay. So what's A of t again? Let's see. A of t is this, which I will just copy. I think I already have it copied, but whatever. So I take this, 2 times this, 2 times that derivative, equals the derivative of E as a function of time. Okay. There. Is that E as a function of time? E as a function of time, yeah. Okay. So what's a constant here, quickly? Well, this is a constant, this is a constant, this is a constant, obviously. That's a constant, the negative sign's a constant. Okay, so the derivative of this, I should be clear, this is d that by dt and d that by dt. So 2, okay, pull the constant out. AI. Derivative of e to the something is e to the negative bt over 2m times the derivative of the top with respect to t. So that's just times negative b over 2m. Yeah. Okay. I think I did that right. Okay. Now the derivative here, well, this is all constants. Yeah, that's all constants. So it's 1/2 k ai squared. Doesn't look like it's going to be the same. And then the derivative is e to the negative bt over m times negative b over m. Okay. Not equal. These are not the same things. This is ai e to the negative bt over 2m minus, or times, negative b over m equals 1/2 k ai squared e to the negative bt over, that's fine, whatever, times negative b over m. So these parts are the same, but these parts are not the same. 1/2 k ai squared. Is that the correct E of t that I got? Yeah. E of t is that. And this is A of t. Did I copy A of t right? Yeah, we got the right answer with it, so. Yeah, we got it right. Did I take my derivative wrong? Did I make the equation wrong? Let's see. Show that in general the fractional rate at which the amplitude decreases in a harmonic oscillator is 1/2 the fractional rate at which the energy decreases. Yep, that's what I wrote here. So then AI is, yeah, that looks right to me. So then this is going to be the constant out e to the negative bt over 2m times the derivative of the top, which is negative b over 2m.
Are you sure that it's going to be 2 times our amplitude?
2 times this?
Yeah.
Yeah, well, it's essentially this. So this is half of this. But that's equivalent.
Read.
Yeah.
So amplitude decreases is half of the rate at which that increases. Yeah. That looks like 1/2 a derivative of a to me.
Look, it should be the 1/2 here.
Yeah.
The
That
thing
would
is
that would make up for the half that we're missing, but I don't get where we're getting, like, we have an extra k there still, and the ai squared.
but hold on, this is now saying that the fractional rate at which the mechanical energy decreases is equal to 1/2 of the other one, which is the opposite of what we want to say. Right? This is saying that the fractional rate at which the amplitude decreases
Is half of the other one.
is half of this one.
Yeah.
Right, so that should be like this. Is half of this. Which is equivalent to what I said before.
I'm interpreting that in a different way than you are.
Yeah. I was confused at the start too. Did anybody else?
I'm almost... Okay,
No,
wait.
no, yeah, you have it right. So you just if you read it out loud, just what the equation says.
Yeah, 2
Yeah, 2 of the fractional rate of which the amplitude changes is equal to the fractional rate of how the energy changes.
Or
So which is
right,
exact.
to match the
Yeah.
question a little bit better, put it like that, right? The fractional rate at which the amplitude decreases is 1/2 the fractional rate at which the mechanical energy decreases.
So the fractional rate of the amplitude decreases on the left side, and it's equal to 1/2, right? Because that's what it reads. Is 1/2 the fractional rate at which the mechanical energy decreases. So it's equal to the 1/2 of the fractional rate. That's why the 1/2 is on the other side.
Yeah.
But yeah, no, either way though, when you follow through with the question, I'm not too sure how we got it wrong.
The answer is 1/2.
The answer. Wait. What? Wait.
The answer to yeah, I can post it if you want.
Sure. Hold on. How's the answer 1/2? Show that in the general. It doesn't even ask for a number. Am I missing something in the question? Let me find it here.
Sorry, the ratio is 1/2.
Oh, the ratio is 1/2. Oh yeah. Okay. Oh. Oh, maybe. No, but we still are gonna have. Hold on. We're still gonna have.
I put in homework help.
Yeah. Let's see. Oops, open Word by accident. Oh, there. Oh. Wait. Yeah. I'll put it on screen. Why am I looking at it off screen? The amplitude of the damped harmonic oscillator is that. The rate of change of the amplitude is that. Is that what we got as the rate of change of the amplitude? Yeah, AI. Oh no, that's not what we got. Wait, what happened to the B, the E to the whatever? dA by dt is A naught.
They have a weird notation. That's the only thing. That A is representative of the entire equation there.
Oh, A of t. This becomes.
Yeah, that capital A is representing A of t.
Oh, okay.
The function, yeah. You're saying that we have an
Yeah.
extra thing on
Okay,
top.
I see. Yeah. So the fractional rate is the derivative per what?
They just brought the A to the other side, and then I think the damped harmonic oscillator is given by that's
Well, they do a similar thing, and then they take the two. So then I don't know what the fractional rate is. Then that's the problem. We don't know what's the fractional rate, because that it's not the rate per time. It's the derivative per the function. Is what they wrote here. The derivative per the function. And again, they said the derivative per the function is that. Sure. I guess. I don't know what the fractional rate at which the amplitude decreases in a damped harmonic oscillator. Let's look up what's fractional rate. Oh, this biology is what it gave me here. Yeah, it just means it doesn't mean what I'm saying. Fractional change. Oh no, there you go. So I just got this from online. Fractional change. Consider a variable x that changes by dx during a period delta t. The fractional change is delta x by x. Okay. Yeah, sure. I don't know. So that's what we're supposed to do. So we're supposed to do dA by dt by a by dE by dt by e, and we're trying to show that this is equal to a half. Or in other words, that matches the question better. That. Right, so the fractional change of the amplitude is equal to 1/2 the fractional change of the, whatever it's called, the total energy. And just to be clear, this is A of t, E of t. And that's what they did. Maybe I won't write it because it's here already, so you can just see. But they find dA by dt, like we did, right? So that's dA by dt. So what they got here is dA by dt, or I'll write like this. dA by dt equals negative b over 2m times A of t. So what they wanted for one part was that, right? That's this. And then the other one is similar. They found this, which is that dE by dt is equal to negative b over m e. Sorry, my phone's thinking. Okay. Good. So, and then again, this is again E of t. So similarly, we can find dE by dt by E of t is equal to negative b over m. And then we just take the ratio of these two things. So this quantity was, sorry, this was, yeah, no, that's right. That top quantity was negative b over 2m, and the bottom quantity was negative b over m. So most things cancel, right? Now we're trying to show this is equal to a half, so 1/2 equals a half. And that's it. So it's just we didn't know what fractional change was. I don't, yeah. Any questions about this one? Any questions? Okay, I think we're good. Sorry, just give me 1 second here. Okay, let's do the last question from this bit, and then I'll take a short break after that. So let's see. I don't know where my questions went. So we just did number, what did we just do? Number 40. So the last one is number 47 from chapter 16, or from chapter 15.
Are you doing chapter 16 today?
Yeah, we still have some time. We go till 8:30, so we still have some time. So yes, the answer is yes. Okay, this is the last question, so let's see how well we can do it. From last question from chapter 15. So let's take a look. Particle with mass that is attached, so m equals 0.5, is attached to a horizontal spring with a force constant of k equals 50 newtons per meter. At the moment t equals 0, the particle has its maximum speed of 20 meters per second. So it's at the max. Sorry, it's at the maximum speed. So t equals 0. Well, I'll say v of 0 equals 20 meters per second equals v max. Okay, and is moving to the left. Oh, it's a horizontal spring. I guess we have to define which way is positive. I guess to the right is positive. That's what they want us to do. Let's just say that, I guess. Okay. Determine this particle's equation of motion specifying its position as a function of time. Okay. What's its x position as a function of time? Well, in general, it's a cos omega t plus phi. Right? Omega t plus phi. Okay. Well, we know that omega is k over m, right? Yep, k over m. So we can right away say omega equals the square root of k over m. I keep forgetting to say square root. So 50 over square root of 50 over 0.5, which is going to be some like 10 or something. 50 over 0.5. So 10 is going to be 10. So omega equals 10. Okay, and then the amplitude. Well, okay, we know Vmax. So we know... yeah, okay, I see. So Vmax is A omega, right? A omega equals Vmax. Well, we know that Vmax is 20. So we know A omega equals 20. So the amplitude is 20 over omega. Sorry, I wrote 10. I wrote omega there instead of 10. It's supposed to be 10. So 20 over omega, which is 20 over 10, which is 2. So our thing as a function of time is a cos omega t, a cos 10t plus phi. And by a, I mean 2. Wow, didn't put any numbers in that first time. 2 cos 10t plus phi. And now we just got to figure out that phase constant. So it's moving at t equals 0. It has the maximum velocity. And it's moving to the left. Yeah. So if you imagine what it looks like, well, okay, so our, this is our x of t. This is our x of t. Our v of t is just going to be negative 20 sine of 10t plus phi, right? And at t equals 0, right? At v equals 0. At t equals 0, this is 20. So negative 20 sine phi. Right? So the speed, we just know that the speed at t equals 0 is 20. So I can just plug that in here and solve for phi. Right?
Can't we just change that original x of t into a sine formula and just call it a day? Because sine starts at its equilibrium position, and that's where our max velocity is going to be.
Still wouldn't quite be right, I think, because we're going to see that phi is not going to be pi over 2. Well, let's try it and let's see what happens. Oh, no, it will be.
Intuitively, because if at t equals 0, it has the maximum velocity, that means it's at equilibrium.
Yeah, you're right.
Left.
The thing is it's going left in the negative. I guess I'm
calling
that the negative. I'm calling that the negative direction. Yeah. Well, let's see here what happens. So it's going to be sine phi. Sine inverse of negative 1 equals phi, which is going to be pi over 2. No, not pi over 2. Which is going to be negative pi over 2, which is 3 pi over 2.
Yeah.
And it's going to be
because it's going to be negative sign. Yeah, it makes sense.
Yeah, that's what it would have to be.
Mm-hmm.
It would have to be that one. So then there you go. Then that's our x as a function of time. So that's 2 cos 10t plus 3 pi over 2. Yeah, plus 3 pi over 2.
Yeah, sorry about this question though. Aren't there 2 instances where sine would be negative 1?
Yeah, there is.
So how come we chose 3 pi over 2?
So C
exactly
T, right? So yeah, okay. So where's sine negative? Sine is negative here and here.
Mm-hmm.
Right? So we chose 3 pi over 2. That's this angle.
Yeah.
That, right? So the angle, sorry, just to be clear, that's this angle, right? The reference angle is pi over 2. That's this angle here, right? the reference angle is pi over 2. So how do I get a pi over 2 angle into the third quadrant? Well, it's pi plus pi over 2, which is 3 pi, wait, no, pi plus, yeah, which is 3 pi over 2. Yeah, that's this angle. Sorry, I made a mistake.
It's just the vertical, no?
With the vertical what?
Isn't sine?
It's supposed to be along the y-axis.
When sine's -1, it's supposed to be along the y-axis, no?
Yeah.
What's supposed to be along the y, like this? Oh,
Like the arm that we're
this
looking
angle?
at. Yeah.
Your C angle, yeah, it should be along the y-axis towards the bottom half.
Towards bottom, yeah.
This is the first time I'm ever hearing you don't measure it against the x-axis. I've always measured it against the x-axis.
Okay.
No, we mean like
we do, but it's pi over 2. It's negative pi over 2. Pi over 2 is 90 degrees.
yeah. So this would be 270 degrees. Right?
Oh, okay,
Yeah.
okay.
You're just saying
Pi
like
over
the
2. Yeah. Okay, this is this.
Yeah,
This
yeah.
is
There you go.
this is all the way up here.
Yeah,
Right?
that's the only reason it has one solution.
Oh, I see. Okay, that makes sense. Yes.
Mhm.
I didn't even see that. Yeah. Okay. There we go. So that's why, because there's no other way to write that angle. 3 pi over 2 is the only answer. Is that the answer in the book too? Do I have 40? Oh yeah, I have 47. Let's see it. Yes. No. No, they use pi over 2. Okay, the reason they do that is just because they said this was positive. They just said this was positive. I don't know why they said left. I guess I don't know why I said this was positive. So, sure, that's positive. So this is positive. So this is positive. So this is pi over 2. So this is pi over 2. And that's the only difference that was created there. Oh wait, no, how's that positive?
So as long as the phase constant is positive, it's moving to the left. But whether it's 3 pi over 2 or pi over 2, it wouldn't matter.
I swear the phase constant doesn't like dictate anything about direction.
It dictates how it goes from t to 0.
Yeah, well, so if you have like, okay, so if this is our position curve, right? If this is our position curve, and then this is our velocity curve. Boy, can I do this? This is our velocity curve, right? Because this is the derivative, right? So if this is our x of t, then this will be our v of t. So you see that, well, initially we're moving in the positive direction, right? I can change the phase constant. I can drag the v of t graph to be like this, right? To look like that. And now I changed the phase constant and it did affect it, because now we're still have the same velocity, but we have in the negative direction. We have a negative velocity now. Right? So that's why the phase constant does change it here. Okay, so what was I saying here?
They still took right as positive. Because when we graph it, that when you do plus pi over 2, that means it's gonna go down first. But when we did it, we did 3 pi over 2, which made it go up first into the positive.
Yeah.
So 3 pi over 2 would push it push the cos over more than.
Well,
Wait.
yeah. Let me go back here a little bit. So that's the original. 3 pi over 2 would move it to just be a sine graph.
Yeah, but going upwards, not a negative. We're looking for a negative sine graph or a cos plus pi over 2.
Wait, no, but adding 3 pi over 2. Yeah, if our 3 pi over 2 should give us negative pi over 2. Is it sine theta minus pi over 2 equals cos theta, right? Do I have it in front of me here? Minus pi over 2. Yeah. No. Wait, let's just look at it here for a second. This, I want to take the sine and I want to move it in the negative direction. Yes, by pi over 2. So this is what the case is. Okay, so I'm confusing myself now because I got the wrong thing here. Oh, okay. Sorry. Give me 1 second, guys. Okay, maybe let's take a 1 minute break. Someone's at the door. So, give me 1 second. Oh, there we go. You see who's at the door. So, I'll be back in just a second. I gotta just help her with something. Okay, so 2 seconds, guys, and we'll finish this question. Okay. You say AFK. We'll say that. Well, I'll be back in literally just 2 minutes, so I'll just leave it on the screen. Give me 1 second, guys.
Yo, who's ready to fail? Half these questions aren't intuitive.
I'm ready to fail.
Vikram, can you do the questions I sent in chat? Thanks.
Sure, 1 second. Okay. A truck passes at 36 meters per second. If the frequency of the siren. Okay. I'm not too well versed in sound yet.
It's just yeah, I mean not me either, but like the way they solved it is
Mhm.
both of them are moving towards each other, but they're not, right? It says after.
Passes.
It says
What's the frequency heard by
in the
an
truck
observer in the
after.
truck after the police car passes the? So it has a certain frequency, and then the police car is moving in the opposite. So here's the thing. The part that gets you is the frequency of the siren is relative to the police car.
Mm-hmm.
So that frequency does not take into account that it's moving at 45 meters per second.
Okay.
So that frequency is stationary because it's relative to the police car. Because that siren traveling on top of the police car is going to be it's not traveling. Like it thinks that it's not traveling because it's relative. So if you're hearing it, you have to take the relative motion of the truck to the police car, and then you can get your hertz from there. So if it's going 36 in one direction and 46 in the other, that's 4 plus that's 9. It's going to be going 9 meters per second towards the opposite
Okay,
direction.
I don't really get it. Adam,
Okay.
you can carry on. Thanks.
So we'll do this, and then we'll probably get to that question after we get to go to chapter 16.
Okay, got
Yeah.
you. Thanks. Bye.
Adam's back. Let's go. You're muted, by the way.
I was muted. I see. Okay, I'm back now. So let's see where we were. So we're finding the equation, finding the phi value. We want our initial velocity to be negative because you're traveling to the left. You said before that they chose this way?
Yeah, but they chose the same thing that we did.
So then our initial has to be negative.
Take a quick look in homework help. I sent the 2 graphs that I was referring to with the 2 equations. Because if we did 3 pi over 2, it would mean that we're going upwards in the positive direction, which they did not specify. So they're still taking the left as a negative because they want us to go downwards.
Hold on, this is the...
Like, I got rid of the... What's it called? I got rid of the extra stuff because...
Yeah, I see.
Yeah.
But we want our... That's the graph of the velocity, right? That's the graph of the velocity. So...
Position.
Oh, that's the graph of the position. So then,
yeah, because it's close, right?
Yeah. I just got confused. So then the velocity would be maximum and negative. So we'd want it to be, yeah, we want the,
Can you scroll up a little bit?
yeah.
Okay. Initially it's going to be negative.
Yeah, we want pi over 2. Yes, we want pi over 2. Because we want, at t equals 0, we want to be heading downwards.
Yep.
Right? We want to be heading downwards. So to make that happen, it's a shift of pi over 2 for cos.
Oh, I think you set up the v of t equation wrong. Because, we're talking about velocity, like... Wait, never mind.
Oh, wait, this would be, oh yeah, this
Never
would
mind.
be negative cos.
Never mind. Okay. Wait. It is supposed to be negative.
So this would be negative 20. That's why that's positive 1. Yeah, this works now. This works.
Okay. Yeah,
This
yeah.
works. And we'll get this out. And that's our, yep, that's right. Okay.
Wait, how'd you get negative 20?
Because the
Wait,
velocity
wait,
is,
negative
20, but we have to be heading to the left to start with.
Yeah, got it.
So the velocity is negative 20.
Okay.
Okay, and then, that's part A. So then part B is where in the motion is the potential energy 3 times the kinetic energy? So we want to know. Where's the what? The potential energy. Oh, wait, no. Where in the motion is the potential energy 3 times the kinetic energy? So the potential energy, I'll say U, equals 3 times the kinetic energy. Okay, so U as a function of the position. The potential energy as a function of the position is the kinetic energy is 1/2 mv of t squared, right? The potential energy is 1/2 k. Do we have a k? Yeah, we do have a k. 1/2 k delta x squared, which is just x of t squared. X of t squared. Yeah, and then solve for t. Okay, this should work. Let's try it. So then this goes here, and then this is k x of t squared, so it's 4 cos squared 10t plus phi. So 4 cos squared 10t plus pi over 2 equals 3m, and then v of t squared. So 400 sine squared times 10t plus pi over 2. So now solve for t. So it's going to be, I'm going to divide both sides by cos squared. So 4k equals 3m, well, I'll say 1200 m. It'll be a tan squared 10t plus pi over 2. And then, so it's going to be 4k over 1200 m. Well, the square root of that is tan of 10t plus pi over 2. So then we need to say, I think we just take we don't have to worry about different solutions to tan inverse here. I think we can just worry about the first one. So I can just say tan inverse of both sides. So it's going to be tan inverse of the square root of 4k. Well, that's going to be k over 300. Yeah, 300m equals 10t plus pi over 2. So divide both sides by 10 and subtract pi over 2, and we get t. So let's give it a try. Let's see if it works. So tan inverse of the square root of k, which we said was 50, and m is 0.5. So 50 over 0.5 times 300 over 10 minus pi over 2 And I got t equals negative 1.518. So maybe we do have to worry about different solutions for tan here. Yeah, we think we do. So I doubt that's the answer. That wouldn't even make sense. No, because no, that wouldn't make sense. There's no way. So I guess we tried to consider the two different solutions to tan. So, yeah.
I think you divide that pi over 10 also.
I might have what, sorry?
Divide that pi over 2 by 10 also.
Oh yeah. Wow. Okay, too much in my head, I guess. That's why. Okay. Yep. And let's see if that fixes it. Well, I still got a negative number. So negative 1.0110. Oh, no, sorry, 105. Still got a negative number. All right, I guess could have just done that, but yeah.
Could you scroll up a bit higher, just to the beginning of the solution?
Yeah.
Yeah.
But to here, I guess.
Yeah.
Yeah, I think I just have to consider the different values of tan inverse here. So I think the problem is this section. So let's just say theta. Oops, just say theta equals 10t plus pi over 2. So we're looking for, and I'll find this number. What's the square root of? It was k, which was 50 over 300. No, 300 times 0.5. So root 3 over 3. Okay, so where does tan theta equals root 3 over 3? Well, yeah, okay. If I just do tan inverse of root 3 over 3, no, it's not root 3, yeah, root 3 over 3, I get pi over 6. So theta equals pi over 6. So CAST, so tan is positive here and here, so pi over 6, so I want to do pi plus pi over 6. So pi plus pi over 6, and I get 7 pi over 6. No surprise. So it's also 7 pi over 6. So let's see if that works. So I'll rearrange this again. Yeah, I'll rearrange this again. So it's going to be, well, from here. If I do tan inverse, root 3 over 3 equals theta. So I'm going to say 7 pi over 6 equals theta. 7 pi over 6 equals 10t plus pi over 2, right? 10t plus pi over 2. And then, so subtract pi over 2. So 7 pi over 6 minus pi over 2 over 10 equals t. And let's see if this is any better. Answer minus pi over 2 over 10. Okay, good. I got a positive answer. So 0.209 seconds. And does anybody have the answer for this one? Do I have the answer for this one? I do. Let's see. For which part are we doing? B? Oh, that's not what I got. Not what I got. Oh, wait. What? Did I get... Wait. I just say pi by 6. No, it's still not right. Okay, I thought for a second. Wait, is this part C that I'm doing? Somehow we got the answer to part C, but whatever. No, not really the answer, I guess, but just a coincidence that this number. Okay, so where in the motion is the potential energy 3 times the kinetic? Yeah, we didn't get B. That's not what B is. Oh no, this is the time. Hold on. This is the time that it took. 0.209 seconds. Right? But this is where in the motion is the potential energy. So let's plug that into x of t. So it's going to be 2 cos 10 times 0.209 plus pi over 2. And yeah, there we go. Now I got the answer. So the answer is, so I'll call this t naught. So x of t naught is, well, I got negative 1.736, but the answer here is plus or minus. That's the number in the book. So I guess that makes sense if it's, yeah, okay. You were at the maximum velocity and then you move, so it's like somewhat of like a equilibrium point. So yeah, there you go. Okay, that is the answer. Then let's try part C. So find the minimum time interval required for the particle to move from that to that. Just okay. Well, if this is 0, then this must be plus pi over 2.
So is minimum time redundant? Could I just have been find the time interval?
I think so. I think I can just say 1 equals 2 cos 10t plus pi over 2. So 1/2 equals cos 10t plus pi over 2. And then I just say cos inverse of a half minus pi over 2 over 10 equals t. Let's see if that works. So cos inverse of a half minus pi over 2 over 10. I got not the answer. Maybe now we have to consider different. CAST, where is it's a positive number, so it's positive here and here. So I want to do 2 pi minus that. 2 pi minus that. Still not the answer. Okay. The minimum time interval required for the particle to move from x equals 0 to x equals 1. But isn't that just a set time? Because cos of pi over 2 is 0, right? Yes. Let me check that. Yeah, it's up here. Yeah, cos of pi over 2 is 0. So, yeah, that would work because t of 0 is 0. Or x of 0 is, when t equals 0, the x position is 0. And when t is 1, the x position should be this. Right? 1/2 cos inverse of a half minus pi over 2 over 10 equals t. Yeah, and I get an answer, but it's not the answer. It's also still negative, which isn't a good sign, but over 10.
Oops. Do we also have to solve for t when this equation is equal to 0, not 1? And then find the difference between those?
But the thing is that when this equation is equal to 0, t equals 0.
Really?
Yeah, right, because, well, let's try it. if I say 0 equals 2 cos 10t plus pi over 2, right? Okay, so the only way that like we can solve it, but just like logically here, well, how can this be equal to 0? 2 is never 0.
It would be 0. It would
Right,
be
that
0.
has to be 0. So, right, it would be with t equals 0. So it'd be, so the value I get here is,
Oh, hold on. Couldn't you also find two instances when cos has a y value of 0? Because it wouldn't just be
yes,
pi over 2, right?
yeah, it would be 3 pi over 2.
So then if you minus, so 3 pi over 2, and you minus pi over 2,
Wait, why minus
and
3
then
pi over 2?
because then when you move over the pi over 2 on the,
Oh, yeah,
the
yeah,
other
sorry,
side,
yeah,
and then you divide that by
well,
10.
0 point pi, really. I don't know why it's 0 point, no, I guess.
And then I get 0.314 seconds.
Which
So
is
then
the
could you
answer, though.
subtract? No?
No, yeah. Good idea. I did that too, yeah, but no, it's not the answer either. 3 pi over 2 minus pi over 2 over 10.
Hmm.
Yeah. Maybe could someone try to find it on Slater? Or did someone post anything in discussions here? No, doesn't look like it.
I can post it. Just give me 1 second.
Yeah, okay, sure. What are we missing? Anything we're missing? Oh, this is, I'm looking at the wrong part. I was trying to understand the wrong part.
It's B, C, A.
This is part C. This is part C. Two, is that our equation? 2 cos, went too far. No, I didn't go too far. 2 cos 10 plus 5 pi over 2. 2 cos 10 plus 5. And I want to know when that position is 1. So the t, the time interval to get there. Yeah. No, that's right. Oh, here. Okay.
I put it in.
Thank you. Yeah. Let's see what we got. We are given that, yes, equation for the motion. Okay. Wait. For x equals 0. Wait, we got that, but not by. Oh wait, this is our equation for motion.
Yeah, I think I think what they did is they added it instead of subtracting their final answer.
Yeah.
Because we got 0.314, right? That's when we set it equal to 0. And
yeah.
when we set it equal to 1, did you get 0.5? I didn't do the calculation myself, but did you?
No. When we got 0.314 when x equals 1.
Oh, I thought it was when x equals 0.
No.
That's what it's showing right here.
Yeah, we got it when x equals 1. Right.
Hold up.
When x equals 1, we solved this, and then from this we got one solution was this, and the other solution was. Well, I can't erase now for some reason. Okay, there we go.
The solution was 0.314?
Yeah, that was the second solution, yeah.
Oh, because when I was solving for when the position was at 0, so when x equals 0, and I was solving for t, I got 0.314 as well.
Wait, how? Are you using a sine function or a cos function?
Cos function. So what I did is,
yeah.
so I set it equal to 0, right? and then I had to do the cos inverse of 0, and that got me pi over 2. So what I did is I found two instances when cos cos is equal to 0, its y value is equal to 0, which is also 3 pi over 2, not just pi over 2.
Yeah.
So yeah, so when I had 3 pi over 2 and I minus pi over 2, then I was just left with pi. And then pi divided by 10.
Wait, 3 pi over 2 minus pi over 2 divided by 10 should give you t.
Yeah, and that gives me 0.314.
Yeah, 0.314.
And that's the instance when the position's at 0, not 1.
Oh yeah, then how did we get... Hold on, then that's not a solution for this one. What's cos inverse of a half? Cos inverse of a half is pi over 3. Oh.
What do you think there is?
No, I didn't get this like this. Hold on. I didn't get... Is the cat here? I think I hear the cat chewing something. So, yeah. So this is... for that... So this would then be... Wait. Cos inverse of a half minus... over 2. Hold on. I gotta stop the cat chewing something. I don't know where she is. I think she's under the bed. Where is she? Get out of there. Okay, I got her. We're all good.
All right.
Okay. So what was I doing? This is pi over 2. Yeah, that number. Let me just type one thing in here. I just want to see if I can get it. 2 pi. Yeah, still not the answer. Okay. So just trying to see something if I can do it to get the answer, but it didn't work. Okay, so this is when x equals 0. It's pi over 10. Well, it's pi over 10 pretty much. Times later. Wait, how is it pi over 10? This is 3 pi over 2. Oh yeah, 2 pi over 2. So it's just pi over 10. So, in fact, I'll just write it as that. Pi over 10. That's the next time it's 0. Right? Or on the way down. But that's not... But if we put this t value back in... Yeah, no, we would get 0. Yeah, we would get 0. But I think it's like the next 0. Because our cos function goes... Well, it's really like this. Right? So our cos function... The first 0 is at t equals 0. The second 0 is at t equals pi over 10. Right? But we're trying to go from here to here. We're trying to go from x equals... Well, no. We're trying to go from... What are we trying to do?
Y equals 0. Well, I mean, it's hard to explain, but in this case, our x could be treated as the y. And then the x-axis would just be time.
Let's look at the question again. Minimum time interval for the particle to move from x equals 0 to x equals 1 meter. Wait, how is a particle moving from x equals 0 to x equals 1 meter? Hold on. No. We need something different. To go from x equals 0 to x equals a meter, that's not from y equals 0. Unless this whole time has been x's? Wait, am I just confused? Let's see. X equals 0. Because this should work otherwise, what we're doing.
I think it's just the combination of what values of pi to use. Because you know how when we're doing our inverses, there's two cases, right? We just have to choose the right combination because, like, for example, when we were doing 0, we chose 3 pi over 2, which was the correct solution. We couldn't have done pi over 2, or else that would have given us the wrong answer. So I think we just have to choose the right.
Wait, here? Here? Would it have given us that?
Yeah. So right over here, see how we did 3 pi over 2 minus pi over 2? So that 3 pi over 2 is what we should have chosen instead of the pi over 2, because that would have given us 0. And then time would also equal 0. Which isn't the case in this in our solution. You see how they got 0.314?
Okay, yeah. I see how they got 0.314.
The same thing needs to apply when we're setting the equation equal to 1. When we're doing the cos inverse of 1/2, we have to be able to choose the right value of the two. So like we said, so see how we did cos inverse of 1/2, and that gives us pi over 3. Our other option, our only other option would be 5 pi over 3, right? Because that would be 2 pi minus pi over 3. So let's do that. Actually.
2 pi minus,
So yeah, so if I do 2 pi, sorry, wait. So yeah, so if I do 5 pi over 3, and then we minus pi over 2, and then we divide that by 10, then we get 0.366, which isn't what we need, because we need the 0.5, right? Because that's what the solution has. So if we try it one more time with pi over 3.
Yeah, here, I'll do it with pi over 3. I get
minus,
negative 0.05.
So then we get a negative value. That's what's throwing me off.
Yeah, I know. I'm on the same train of thought too, right? Yeah, it's not doing.
Can I see the solution one more time? The one that you put up on the.
Here.
So yeah, so then 1/2. Oh, they use sine, not cos.
Yeah, they have a different function.
That wouldn't have mattered though, right?
It just changed the phase shift.
Exactly, right?
But also look here, look here. All of a sudden they don't use the phase shift. There's no plus pi here. There's no plus pi. I can't draw plus pi for some reason, but any reason that why would they drop it? It's the same equation. And it changes the answer. Also,
so how come their equation in terms of sine though? Would it matter? Like,
I think that that's just how they did it, because it doesn't say to do it in terms of cos. We just did it in terms of cos. So they just did it in terms of sine, which is throwing us off now, but yeah. But that's okay. What are they solving for here? We're given that at x of 0. So the x position at t equals 0 is 0. So given an equation for the motion,
I mean, I just don't get that statement, because if you look literally right after, we have a time of 0.314, not a time at 0.
Yeah, they said they immediately look for the next time that it crosses the x-axis. Right?
Yeah.
So we know our... Okay, so the equation for this, for the minimum time it would take to go... Wait, we're heading to the... Oh, hold on. Our... Oh, hold on. No. This is what's happening.
Did you...
Yeah, so go for
Did
it.
you just ignore the phase shift because cos theta plus pi by 2 is just sine theta?
Yeah. It doesn't matter that we use cos. That's not the issue.
This is what's happening.
That's the reason they ignored this phase shift.
This is what's happening. This is our graph.
Okay.
Of our thing. We need to figure out how long does it take to get from here to here. Well, it takes 0.314. That's what we calculated. And then it'll take this distance, right? It'll take how long does it...
Your graph is in terms of x and y. I'm picturing the graph in terms of x and t.
This is x and t. So
then that red line that you have at the bottom is the time that it takes.
Yeah,
Not
this
the
is second.
distance that it travels. Oh, sorry. Okay.
This is second. Yeah, maybe I said distance. Yeah, this is the seconds, right?
Yeah. Okay. So 0.314. Yeah.
That makes sense. We got that number, and now we got to find this number. So how long does it take to get from
0 to 1? How much time does it take to go from 0 to 1? Right.
Yeah,
we're
and
trying-
that would be. Why would this not work still though? We solve for it at 1. Why would this not work? This 1/2 thing. Right? That's what's confusing me. Maybe this negative 0.02. Wait, what if I do? No. And is that the answer in the book? 837? Oh, that's also not the answer in the book from this Slater thing.
Wait, what?
For part C? Yeah, for part C of 47. For part C of 47. Yeah, in the answer in the book it says 0.105. But this is kind of making sense so far, so let's just see what...
Did I give you the right solution?
Well, it looks like the same question. They got a different number than like...
It was 47C, right?
Yeah. You gave me the right thing, I'm pretty sure.
Okay.
I'm pretty sure. Because this makes sense too so far. It's this time. So yeah, maybe I did say distance before. This time, right? And then this time here to get from 0 to 1. But what I'm confused, and that's what they do here. That this is the red section well, they're both red, but this is the other section. And this would make sense, except they dropped the pi. They dropped the pi. So I don't really understand, but okay.
So what's the answer we're trying to get? Because you said 0.1 something at one point.
In the book? That's from the book?
Yeah, so the book with the exact same numbers that we have.
Yeah, 0.105 seconds. That's the answer.
And then Slater's telling us something else.
Slater's telling us 0.8376.
Okay.
Pretty different. Let's see if we do it. What was the other answer we got out of this using find it now. Oh, I lost it. Cos inverse of a half was what again? Cos inverse of a half was pi over 3. Pi over 3, yeah.
Okay, so I got my answer to be 0.0525. That's what I got. So what I did is I just minus the time. So you know the time that it takes to get from 1 0 to the next 0, which was 0.314.
Yeah.
Then I calculated the amount of time that it took for going from that 0 to 1, and I subtracted that time.
Wait, why'd you subtract that time?
No, I shouldn't have subtracted that time. 0.314.
So no, that won't work. Plus something's wrong here with how we're doing this, and I don't really know why. Let's see, pi over 3. 0.052. What did you say? You got 0.0523 or something? 524?
Yeah, that was it. That's when I subtracted them, but there's no reason for me to do that.
What was this answer we got? Yeah, 0.314. What's the answer?
What's the equation of our graph, by the way? It's 2 cos.
2 cos 10t
10.
plus pi over 2.
Plus pi over 2. Okay.
Yeah, which is the answer for part A. So we did that right.
Yeah.
And then here we got we got part B too. So that works. And then
Okay, so I am looking right now on Desmos.
Yeah.
And I am checking. Okay. I'm looking at the graph when its x value, or sorry, its y value, I guess, is 0. And then I'm following that line until it reaches a y value of 1. And the difference between those two, here, 0.
let me put it on the graph too here. Let me see Desmos here. So our thing is 2 cos
So 0
x plus
3,
pi
6, 7
by 2
minus pi over 2 over 10 over 10. Yeah. So that was the time that I got as well.
Yeah. So essentially, we're looking for the time.
Or sorry, no, sorry. That's not the time. That's the distance. Maybe that's our issue. Okay. If you look, yeah. So put your mouse.
Yeah. Hold on. This isn't even the answer that from the book. This is none of the answers. The distance. This is the time axis, right? This is the time.
Yeah.
So. Oh wait,
Yeah,
to 1. Wait, hold on, to 1, which is here.
Yeah.
Which
So
still
that is
isn't one of the-
So that's 0.367, and then go back to 0.
Here or to here?
No,
Here?
yeah,
Pi
there,
over
and
10.
then that is pi over 2. Or sorry, pi over 10. Yeah. So 0.367 minus pi over 10, that is 0.0528 seconds, and that is none of the answers.
Yeah. That would be the answer. Pi over 10 plus 0.366. That's how long it takes to get from
Wait,
here.
so plus? Oh, from
Yeah.
that 0. Oh, yes. Yeah, that makes much more sense now.
So that's 0.366. I got 0.68.
Yeah, so did I.
Which still is none of the answers.
Yeah.
But our equation's right. This is the position. We're going from a x value. So remember this, it's confusing. This is the t-axis, this is the x-axis. So we're going from an x value of 0 to an, I mean, they don't actually even say from t equals 0.
They said when x equals 0, right? So then, here, let me.
Then, wait, yeah, hold on.
So that's why I subtracted the times.
Yeah, I see why you'd subtract. Yeah, I see why you'd subtract. 0.366 minus pi over 2.
And then I got the 0.052. I forgot what it was.
Wait, I got some. Oh no, pi over 10. Sorry, not pi over 2. Pi over 10. Yeah, 0.0518.
Yeah.
Which.
That's how many seconds it should take, or the shortest amount of time it should take to go from an x value of 0 to 1. So we didn't do anything wrong.
That seems right to me.
Right? I don't know. I think this question.
Yeah, because here that's that time, and here it's 0.366. So 0.366 minus that's the quickest it can go from 0 to 1. Yeah, 0 to 1.
By the way, are you doing this every night?
Yeah,
until
for the next 3 days. Yeah.
Okay, that's good. That's good. Is this our last example for today?
Yeah, it is.
All right, sounds good. I'm gonna head out.
Yeah. Okay, sounds good. Thank you for your help. Thank you for talking through it.
No, I was just trying to understand it. I didn't really help with all.
No, you did.
All right.
You did. good to talk about it. Okay, have a good night. Okay, let's. Maybe someone should. Okay, maybe the solution is to. Okay, let's go. Let's move on to D, I guess. Let's try to see, can we even do part D without finishing this? Find the length of a simple pendulum with the same period.
I find Slater is wrong, like once in a blue moon.
Yeah.
It doesn't make sense.
I don't know if they're wrong, but it doesn't make sense what they did. It doesn't make sense
Yeah.
to me because...
No one commented under. Usually when it's wrong, someone would comment,
yeah.
But someone did make the solution for A and B underneath, but they didn't include C and D. Maybe there was something wrong with those. That's why.
Yeah. Yeah. So, because I don't know why they dropped the pi. There's no reason for them to drop the pi. They're doing the same thing.
What question is this, guys?
47. 47 from the textbook.
In chapter 15?
Yeah.
Thanks.
Yeah, okay, let's try part D and see if we can do it. Find the length of a simple pendulum with the same period. So what's the period of this? The period is 2 pi over omega, right? So 2 pi over 10 is pi over 5. So the period is pi over 5. Which makes sense. Pi over 5. So now we want the length of a simple pendulum with the same period. So let's take a look at what I have here. Well, it'd have the same omega. Yeah, it would have the same omega. Okay, this is actually a pretty simple question, I think. So for part D, right, we can say omega equals 10. Omega of a simple pendulum is the square root of g over the length. So we can just say 10 equals g over L, like 10 squared equals g over L, right? So L equals g over 100, right, which is 9.81 over 100. Oops, 100. So I'm moving the decimal 1, 2, 3. So it's 0.00981 meters. Which isn't the answer. 1 extra 0. Did I add too many zeros? Move by 1, 2, 3. No, which looks like it should be 2 zeros. 100 squared. Yeah, I mean 10 squared is 100. Divide it. What? Oh, that they just did it wrong.
Yeah, I think you added one. I think you added 1 0 extra, right?
Oh, yeah. What am I doing? How did I do it twice in a row? 9.81. 1, 2. Oh, yeah. I'm moving 3 spaces. I thought I was dividing by 1,000. There you go. That's all it is.
Yeah.
Yeah. 981 meters. There you go. That's the whole problem. Okay. Part C, I will maybe try to ask someone and see if they have any solutions. I don't know. We'll talk about it tomorrow, I guess. I'll try to figure it out. But yeah, for now, then, that's everything for today. Okay. I will be back on tomorrow at 6.